Okay, we are now recording. Stop the video. Okay. All right, so first things first, guys, mock interview signups. They're going to be in early April, I think. The spots are running out. So I think we started with like 60, I think either 40 or 60 slots. I'm not remembering because I didn't set this up personally. Again, this is being done with like my team of people at Facebook. It looks like there's only 6 slots open. So if you haven't signed up already and you really want to, I hope one of these slots works for you. If not, we're definitely talking to see if we can set up like a reoccurring kind of thing, you know, every month or at least once every semester, etc. So please sign up for that. Another reminder, homework 6 is due today at 11:59. Who's already finished it? Yeah, you guys rock. Okay, you're awesome. That's great. I love it. I love it when people finish things early. At the very minimum, it tells me that I didn't mess up on the homework and like things are working. So, all right, homework 7. I'm cooking it up. It is going to be released today at 5 p.m. and it goes over graphs. So we're going to do a little bit more on graphs. So it's going to cover Dijkstra's algorithm. It's going to ask you to run Dijkstra and to like understand how it works. So definitely take a look at that once it's released today at 5. And then we also have a homework party. Just follow me after class, 1 p.m. to 3 p.m. We're just going to head out to the Martin building, the new fancy building. And we're going to try to hijack one of their rooms. I have access to some of the rooms. I emailed people requesting rooms. They did not get back to me, but you know, we will ask for forgiveness after we get kicked out. That's how we're going to work on this right now. And I have a marker. I brought a marker. Yeah, we should be good. Should be good. Any questions on the announcements? Also, in case you guys want to know, Chi is working on writing up some solutions for our quizzes, like detailed explanations. She's already knocked out quiz 1 through 3, I think. So I don't know. It's up to her, but we'll be releasing those like explanations at some point to help you guys study for the final. Cool. All right. So today we are going to continue on dynamic programming. We're actually going to have 4 lectures on dynamic programming. I'm counting the one on Monday as part of dynamic programming because Bellman-Ford is a dynamic programming algorithm, even though you guys didn't know that before. Okay. So today we're going to continue with the Bellman-Ford algorithm. So we're going to review it a little bit. And we are going to explain why it works, how it works. And we're also going to talk about some of the situations where it doesn't work and how to change the algorithm so that you can address those situations. Okay. Again, keep in mind that I haven't told you what dynamic programming is, but I want you to keep in mind that Bellman-Ford is a special case of dynamic programming. Okay. And what we're going to do towards the end is we're going to introduce dynamic programming, like what it actually means, what the technique represents. And we're going to work through a much simpler example than Bellman-Ford, which is computing the Fibonacci numbers. And we're going to show how that is an example of dynamic programming. Cool. So any questions on this for today? You guys feel good? Do you guys remember Bellman-Ford from Monday a little bit? No? Well, if you don't, this is the pseudo code. It's actually 3 for loops. Pretty simple, I would say. And the difference between Bellman-Ford and Dijkstra, for you guys to remember, is that in this first iteration, Dijkstra picks the node smartly. It says like, what is the not sure node that is the closest to me? I'll look at that one and then update all of its neighbors. But in Bellman-Ford, we just say, you know what, just update everybody. Just don't bother picking one node off the table. Just go through and update everyone to update their estimates. Okay. But the update is the same. You take the minimum of your current estimate plus of that and the path to you plus the edge UV. Okay. So why does Bellman-Ford work? We're going to walk through this today. So again, for a lot of algorithms that use iteration, the way you prove that it works is you do an inductive proof. Okay. So inductive proof have 4 pieces. They have the base case, they have the inductive hypothesis, they have the inductive step, and then they have the conclusion. Okay. So the inductive hypothesis here is going to be that div is equal to the cost of the shortest path between S and V with at most I edges, right? So again, just to refresh your memory on some of these terms. So S is our source node. That's the one where we're trying to find the shortest path from S to every other node, right? So all the algorithms we've covered so far are single source shortest paths. So they don't give you the shortest path between all nodes. They just give you the shortest path from wherever you start to everywhere else, right? V, right? So V is our variable here. So this array, we have, wow, these markers are not working today. V is the destination, okay? So dv here is actually an array that's going to contain all the, from S to, from node S to node 1, to node 2, to node 3, to node 4. What is my current estimate of the distance, okay? And what we're saying is if you go back to the pseudocode, right, we have dv ds. So we say the estimate from S to S starts at 0. That's the base case. And then at the very beginning, it's infinite for everything because we don't know. We haven't explored the graph yet. One thing we're going to tweak is you'll notice that in this proof, I added an additional index I here. Okay, the I corresponds to this I. So when you write it in actual code, you do not keep like all the separate arrays. We're going to talk about that a little bit. But in order to talk about the proof, it helps to think as like each iteration, you're making a brand new array D, and you're filling it in using the previous array. Does that make sense? But in the actual implementation, you actually only need to keep one array because the way of the way the updates work. Okay? So the inductive hypothesis is that at the ith iteration, D, so the distance from S to V, whatever number I have here, is going to be the shortest path between S and V with that most I edges, right? That's what we're going to try to show, that is always true, that is the case for every I. And the conclusion is that when we get to n-1, right, then it is the shortest distance from S to V with at most n-1 edges. Why does that give us the shortest distance from S to V? Why do I only have to go up to n-1 edges? Yeah. Yeah. I mean, I think you're going around the right track. So the thing to keep in mind here, the intuition for this is that you have n nodes. Okay. If there's n edges, if you have n nodes and n edges, it has to make a circle. There's no way to have n edges and not have it be a cycle, right? So if you're looking for the shortest path, right? If it has a cycle, it is not the shortest path. You could remove the cycle, right? So any shortest path will be at most n-1 edges long. If it's longer, it has a cycle, which means it's not the shortest. You could remove that cycle and then it'll be shorter, right? Right. So like, that's the idea. So if you have like a path like this and you're saying, oh, this is the shortest path, you would say like, that's not true. Just take this off. Whatever this is going to be shorter. So we're going to talk about it in a little bit. But this is the inductive step conclusion. We're going to do the base case and the inductive step. Okay. So, oh yeah. So this is the aside. Assume there is no negative cycle. So assuming there are no cycle that adds up to a negative value, right? Because again, we talked about last time that if you have a negative cycle, it's impossible to define a shortest path because you just take that cycle over and over, and then your length of your path just gets shorter and shorter, right? So assuming there are no negative cycles, then the shortest path from S to T has to be what we call a simple shortest path. So this is actually what you guys were just talking about right now, right? Which means if I have a path that has a cycle in it, because this cycle is not negative, then I can remove that cycle and make the path shorter, right? So any shortest path has to be a path without a cycle. Okay. Yeah, you just get rid of the cycle. So a simple path in a graph with n vertices has at most n-1 edges. So again, this is important that you know that you are convinced this is true, because that is why we can stop the algorithm after n-1 iterations. Okay. Yeah. Cool. So coming back to this, do notice that negative edge weights are okay, just not negative cycles. Yeah, like I said, a note on implementation, we're going to use this thing where I keep all these arrays around because it's going to help with the proof. But in real life, you really only need these two arrays. You can forget all of these. Like once you're at iteration 5, you just need to know the array for iteration 5 and the array for iteration 4. And actually, you only really need the last one. Cool. So summarizing a couple of pros and cons. So the running time of Bellman-Ford, for each of the n steps, we update m edges. So the running time is mn. So it's slower than Dijkstra. However, it's more flexible. It can handle negative edges. And if we constantly do these iterations, any changes to the network will eventually propagate. So with this, yeah, okay, these slides are a little bit out of order, but I'm kind of covering a lot of stuff. If we constantly do these iterations, any changes to the network will eventually propagate. What that means is that Dijkstra, so for Dijkstra's algorithm, we have to have a data structure that holds all of our nodes and then gives us the minimum value. Okay. So anytime one node's edge changes, everybody else needs to know of that change. For the Bellman-Ford algorithm, it's slower, but it's actually easier to distribute because you only need to know about your neighbors changing. You don't care about something very far away changing. Okay. I guess this is an example of a negative cycle. Let's just go over it. So again, just to be very clear, what's the shortest path from Aggie Village to Aggie Suites in this graph? Six. And what's the path? Okay, so this has cost 6. Great. Can anybody find a shorter path? Serena?
From Aggie Village to Aggie Terrace, then to the clock tower, and the health center.
Clock tower, health center, then this. What's the length of that path? Oh, that is not a possible path. Why is that not possible? You can't go from here to here, right? Okay, so that's not a possible path. Can anybody find another path? So yeah, so that is another path. Aggie Village to Aggie Terrace to Aggie Suites. That path is going to have 7 cost, so it's longer, but it is a correct path. Anyone else? Yeah, David.
Just depends on my answer. So, what direction? Aggie Village, Aggie Terrace, that's just both ways, right?
Oh yeah, that's a good. Let's say this one is. Yeah, let's say it's both ways. Yeah.
We take Aggie Village to the clock tower to Aggie Terrace, go back to Aggie Village. We'll do it like once, twice more, and then go to the health center.
Right. So that's a negative cycle, right? So and that you can actually have the shortest path is just negative whatever you want, because from here is 1, from here it's -2, from here it's -3. So this loop is -4, which means every time you go around the loop, you just get smaller and smaller, right? So yeah, this is the first path. See, so that I don't know if you guys are looking at my slides ahead of time or what's going on, but this is the path that you were meant to find. And just like David mentioned, there is this loop that you can also take that gives you cost 2. And if you take it again, it gives you cost -infinity. So again, I guess just to summarize, Bellman-Ford works with negative edge weights, but it is not okay if there's a negative cycle. However, Bellman-Ford can be used to detect negative cycles. So this does not make the algorithm wrong. It just means that you have to handle the case where if there's a negative cycle, you need to say the answer is there is no shortest path defined, right? So again, if we walk through this example, this is our D. Our D starts at 0, infinity, infinity. What's our next D? Can you guys tell me? What is my D for when I do one iteration of this loop? What does my D look like? Again, one way to try to fill this out. Yeah, go ahead. Oh wait, not 0, infinity. So this is the proposal. How'd you get it so fast? Oh, you just went through the algorithm? Yeah, okay. Just went to the neighbors. All right, so that's the thing to keep in mind. Remember, this I tells you the number of edges your path can use, okay? So for D1, you can only use one edge, which means this D is gonna get filled up only for the elements that are one edge away. So the path from Aggie Village to Ag Terrace is only one edge, which is -3. From Aggie Village to Clock Tower, it's only one edge, which is 1. Everything else is reachable, but it's more than one edge. So it's actually infinity, okay? And that is exactly what it looks like. Who wants to do D2? So again, so D2 is where you can use 2 edges to get, so you're finding the shortest path from Aggie Village to any node that uses at most 2 edges. So I'll get you guys started, which this one's obviously 0. Yeah, David. Okay. Will be 2. Okay. Yeah, 7 because you're using this path, right? Still -3. Anybody want to propose different values? Yeah. Clock Tower will be -5. Okay, you guys, you should be thinking, so okay. So we have 2 proposals here. We have 1 and -5. Which one would it? So first of all, if they're both valid paths, then it'll be the smaller of the 2, right? Because we always take the minimum. So David, do you want to correct yourself or yeah? It's -5 because you can take this -3 and this -2, right? So this actually gets updated to -5. And you'll see that that is exactly what the answer was, okay? So who wants to do the next one, D3? So again, this is, you guys are running Bellman Ford, okay? And again, this should help you build up the intuition that each of these is just looking at the paths that have that number of edges. Yeah, question? You got it? Okay. So who wants to do D3? So if you have up to 3 edges, what are the shortest paths? So I'll give you a hint that I think this one's not 0 anymore. Somebody else other than David, Toby, Isaiah, you want to try it? Jonathan? Yeah, Serena? -4. Okay, do you want to tell us why? Right. So this one is going to be considering, so what it's going to do is it's going to take, so again, if you look at this update, right? So again, like maybe let's try to clarify why it's doing what I say it's doing. It is going to take the minimum of the previous DV. So it's going to look at 0. And what this is telling you is this is the shortest path, right? For any possible path that has 2 edges, right? So it's going to look at that. Or it's going to take the minimum of any possible 2-edge path that has a neighbor coming into the node, plus the edge weight of that neighbor. So that's how we get to the 3 path lengths, right? So this -4 is actually coming from S to Aggie Terrace, which is from S to Clock Tower, which is -5, right? So how are we getting this -4? Is we're getting it from -5 from this path, which we already have the answer to here, plus the edge weight from here to here, which is 1, right? So that's how we get this -4. All right. I'm going to speed this up. Hopefully you guys, or do you guys still have questions? Yeah, Jonathan? Would the health center also update? Yes, the health center would also update to -4, I believe. Do you want to just wrap up the other ones? Sweets. So again, remember though that you can only do up to 3 edges. So I think it's going to be 6. Yeah, I think Aggie Terrace stays the same. I think Sweets turns to 6. Because again, you can only look at paths that have up to 3 edges, and then Clock Tower, I think this one stays the same, right? I'll double check that. I have it on the slides. Yes, that is what you guys came up with. Okay, so we keep going. So the next step is actually going to, well, I guess actually not the next step. So one reason this is not looking so good is that we've actually found a negative cycle, right? But we don't know yet because these weights, we haven't finished our from I to 0 equals to n -2 because it's inclusive. Sorry, that's off. We haven't finished doing all of our iterations. But if we keep going, oh, that's just a bug. That should be n-1. Okay, anyway. This is what the update looks like for the 4th time you do it. And we can tell that it's not a good update, or the 5th update that we do is not good, because if there are no negative cycles, once you do all n-1 updates, this should not change. It should not be possible for your path to get shorter. So again, this graph is 1, 2, 3, 4, 5 nodes, right? So the algorithm tells us to stop here. This should be your answer for the shortest path. Okay. How do you tell that you have a negative cycle? If you run the algorithm for one more step and your values change, then you must have a negative cycle. Okay. So that's actually what you would do. Let's skip this. Let's look at the pseudocode. So that's how you would modify the algorithm to actually handle negative cycles, which is you change nothing, you leave everything the same, except you run it one more time. So instead of only running up to n-2, you run up to n-1 from 0 to n-1, which is actually n total iterations. Okay. And then if the last 2 iterations don't match, so if there's some difference in those arrays, then that actually means the question, what is the shortest path from S to any node, is not well defined because you have a negative cycle. Cool. Okay, so wrapping up Bellman-Ford, we do also use it in practice. So remember Dijkstra, we used it for networking. It's actually pretty common, very frequently used. Bellman-Ford is also used very commonly for the routing information protocol. There's a propagation protocol for the internet that tells you. So I don't know if you guys remember when Facebook went down like a few months ago, and it was down for like almost the whole day. So it was down because the machines that run this algorithm to tell the internal Facebook machines where everybody is were down. Okay, so Bellman-Ford is used very frequently. It's not used as much anymore, but it's still used, especially in stuff related to the internet or networking. And what happens is each router, so each computer keeps a table of the distances to every other router. And then once you have that table, so that tells you all your neighbors and how far away they are, you can periodically run Bellman-Ford to update the shortest distances. And that's how your routers like stay up to date to figure out like, what is the fastest way to send my packet from, you know, my laptop here to the servers that Google has in, you know, Palo Alto, California, right? Like, do I first go to Nashville and then go up to Chicago and then down to Menlo Park, or do I go all the way down to Mexico City and then go up, right? Yeah. So let's recap. Okay, so these are the key things that you guys should remember. Like these might come up in like quizzes or finals. Shortest paths, there's BFS. It is running time n plus m. So we consider this a linear running time algorithm on a graph because the graphs are of size n plus m, right? So even though m can be n squared, right? We call it linear time because it runs in the size of the input, right? But you can only use it on unweighted graphs. This is a negative, okay? The other algorithm you learned for shortest paths is Dijkstra. You're going to run this on your homework 7. You're going to do a couple of examples. This is good for weighted graphs. Its running time is n log n plus m if you implement it correctly. Okay, so this is if you use Fibonacci heaps. This is the running time. You can implement it in other ways, which gives you different running times. But it does not handle negative edge weights. And again, your homework 7 is actually going to get, there's a question on your homework 7 that's going to be released today that asks you about a proposal to make Dijkstra handle negative edge weights. And I'll tell you, it cannot. There is no way to make it handle negative edge weights. Okay, so just keep that in mind when you're doing homework 7. The other drawback of Dijkstra is that's a very centralized algorithm. So it needs to keep track of all the vertices to know which vertex to update, right? So instead of just updating everything, it needs to locally know all the vertex values, and then it picks the smallest one, right? Bellman-Ford is the third algorithm you've learned. This uses weighted graphs, even with negative weights, and it can be done in distributed fashion, okay? But its running time is n times m. So we're getting all the way up to n cubed, possibly. So it's slow, okay? It's not a fast algorithm. That's the recap. You guys got that? You guys remember all of that? Okay. You will never see Bellman-Ford in an interview question, just FYI. So you can forget how it works, but it is a nice algorithm. All right. Bellman-Ford is actually an example of dynamic programming. For the rest of this lecture, we're gonna cover something which is computing the Fibonacci numbers. And we're going to show how to compute that using dynamic programming, okay, to give us a better running time. So first, we're going to cover what is dynamic programming exactly and why it's called. Well, we're gonna end with that because dynamic programming is actually, it's very interesting history as to how it got its name. I'll let you guys know. So who remembers what the Fibonacci numbers are? Of course, Jonathan remembers. Who else remembers what the Fibonacci numbers are? I think Leander seems to, he kind of thinks he remembers, but he's kind of bored. He's on his phone, so it's fine. Isaiah remembers. David, yeah, okay. So who, Isaiah, you tell me what the Fibonacci numbers are.
Okay. Isn't it like you take the number and then like you multiply a number that came before it?
Very close. It is not multiply. Yeah, you add the two numbers before you to get the current number. So, yes, it does. And interestingly aside, we're going to cover an algorithm that's really fast. There's actually a constant time solution to this problem, but only if you are into math, which you know. So anyway, but you're right. It has to do with the golden ratio. So the definition of the Fibonacci number is recursive in nature. It says the nth Fibonacci number is whatever the n minus 1 was plus the n minus 2. So the two previous numbers, add them together, that gives you the next one. Okay. And for this case, we're actually going to start with f1 and f2 equal to 1. So you have to give it a starting position. So the first two are 1. What's the next one? 2. What's the next one? 3. What's the next one? 5. What's the next one? 8. What's the next one? 13. And then 21, 34, 55, 59, 144. Okay. So again, this is like, you will not see this algorithm. Like you don't use this software engineering, but this is going to help us understand dynamic programming. So everybody understands how these are computed. Yes. Okay. So the question is, if I give you the number n as input, I want you to tell me what is the nth Fibonacci number. So if I give you, if I gave you n equal to 7, I want you to tell me 13, because that is the 7th Fibonacci number. That is your algorithmic problem. How would you guys do this? That's your interview question, warm up. Yeah, in the back.
Starting with an early game, go down first, like 1 to 0, and those two, I don't know.
Well, yeah, so you're already jumping to a very efficient solution. Well, hopefully you're talking about an efficient, so you're doing a bottom up. Another way to compute it, which is more dumb, I would say, is you can just write it recursively. You can just say there's two base cases. When n is 0, return 0. When n is 1, return 1. Okay. Otherwise, call yourself on n minus 1 and call yourself at n minus 2. Get those two numbers, add them up, and then that gives you the nth one, right? Very straightforward, very simple. So the running time of this algorithm is actually very bad. Who can explain why? Yeah, Jonathan, give it a shot.
Isn't it because you still basically have to go through and find the two before it. So if you have a large set of numbers, you're going all the way through that set of numbers to find the two before the one you're attempting to get to, and then you have to add those two together to get.
Yeah. So you can imagine, yeah, that's the basic idea, which is this recursion here. To calculate the n minus 1, you're going to have to call yourself twice on n minus 2 and n minus 3, right? To calculate n minus 2, you're going to have to call yourself on n minus 3 and n minus 4. Okay. So it turns out that this implementation actually has exponential running time, and not because it's doing anything interesting. It's really just adding two numbers. That's all it does. But it calls itself so many times that it's exponential. I guess there's a graph if you implement it of how exponential it is. And the main reason is like, here's an example of computing Fibonacci of 8. You'll notice that to get 8, you have to compute 6 and 7. To get 7, you have to compute 6 and 5. To get 6, you have to compute 5 and 4. Okay. So you end up getting this tree where like you're doing very little work, but you can imagine at the bottom, you're going to get a lot of very little work. Okay. So can somebody notice like, how might you improve this? Does somebody see some like wasteful stuff that's going on in this tree? Yeah, I say. You're doing a lot of the same calculations over and over again, right? So I think I have a slide that does this, but you know, computing this 6, you're actually computing it here too. And the answer should be exactly the same, right? The 6th Fibonacci number doesn't change just because I computed it 2 times, right? It's always the same. You know, this 5 gets computed here, here, and here. So you're computing it 3 times. That seems wasteful, right? And it gets worse the further down you go. This 4, you compute it here, 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 here. You compute it 5 times, and they're all repeated. So ideally what you would want is you would want something like this, where you only compute each n number once. Okay, so you guys might already, I think Leander in the back was already suggesting an algorithm that is kind of taking advantage of this rather than the recursive version. Okay, this would be better. You know, it's take this tree, but only compute everything once, right? And then to compute 8, I just need 7 and 6. To compute 7, I need 6 and 5, right? But only do it once. This is a much faster Fibonacci implementation. Okay, so it is not doing recursion. It is instead using dynamic programming to fill in your answers bottom up. So what it does is it first creates an array that has the answers for the nth Fibonacci number. For the 2 base cases, we know the answer is 0 and 1. For everything else, we set them to infinity, we set them to none, we set them to something that it's like, we don't know. We don't know the answer, right? It's null pointer, it's -1, right? Whatever you want it to represent. And then what you do is pretty simple, actually. To compute the second value here, you just need to add these 2. And then you put it in here, right? So what's going to happen is I'm going to write 1 here. With the first iteration of this loop, I'm going to put a 1 there. And then to compute this number, I'm just going to look at these 2, and I'm going to write 2, right? What's the running time of this algorithm? It's O of n. Why? Yeah, all it does, it has a for loop that iterates n times, and each time it adds 2 numbers. So it's O of n. How much space does this algorithm use? Yeah. O of n. Yeah. Why? Right. You create this extra array of size n. How might you use less space? Do you need the whole array? Yeah, go ahead. Yeah. Right. So then that's still going to be O of n, right? Because we're still keeping the whole array. Yeah. Yeah. So if you notice, to calculate the ith number, you only ever need the last 2. So if you wanted to, you don't have to keep the whole array. You can forget about the other numbers as you go along. So you can imagine you can implement this actually with just 2 variables, which is what is my previous Fibonacci, my Fibonacci number 2 steps ago, my Fibonacci number 1 step ago, and then you just update those 2 variables in your for loop. So that actually gives you a linear time algorithm to compute the nth Fibonacci number that uses constant space because it uses 2 variables. Why might you want to do it this way? Yeah.
They wanted to repeat the Fibonacci factors for other numbers so you could find them in the array.
Yeah. You might want to do it this way because if you keep the array around, then once you have the array, if anybody asks for like, you let's say the first time they ask you for the 1000th, you give it to them, and then they ask you for the 12th, you wouldn't do anything. You would just look it up in the array, right? Cool. So this is much better running time. As an aside, I don't know if you guys want to take a look at this, but it is actually possible. There is a closed form formula for Fibonacci numbers using some like matrix algebra and stuff. You can actually compute the nth Fibonacci number using the golden ratio to the nth minus the golden ratio, the inverse of the golden ratio to the nth. So you can like do it in constant time. Okay. So again, we're not going to cover why that works. This requires some knowledge of linear algebra is the way this slide is doing it, but just an FYI. So actually what you guys just saw was an example of dynamic programming. So going from the recursive solution, which is doing this like whole tree, noticing that there's a lot of computation that you're reusing, and instead writing it as an array where you save your answers, that is dynamic programming. That is the method that a lot of algorithms use to get faster running time. Okay. So let's actually talk about what dynamic programming is. It is an algorithm design paradigm. Okay. So this is similar to divide and conquer, right? It is a method through which you can solve many different problems, right? Usually we use dynamic programming for solving optimization problems. So if somebody ever asks you a problem, which is like, what is the maximum possible cost of something? Or like, how many items can I fit into a bag? Or like, what is the minimum? Like if you see minimum, maximum sort of things, you should think this might be dynamic programming, right? Like to get a good solution, I might use dynamic programming. Again, the shortest path is actually an example. Fibonacci numbers aren't optimization, but whatever. Okay, so for dynamic programming, this is what you're looking for when you see a problem. For dynamic programming to be a good approach to solving that problem, that's actually going to help you. So the first thing is you need to find something that we call optimal substructure. Okay, so what that means is that similar to divide and conquer, the big problem can be broken up into sub-problems, right? So this is like for free with Fibonacci, right? Because f of I, by definition, depends on 2 smaller f of I minus 1 and f of I minus 2, right? So you have 2 subproblems. If you have the answers to those, it's very easy to get the answer to the next one, right? But this is also true for Bellman-Ford, because the shortest path with at most I edges consists of the shortest path of I minus 1 edges and 1 extra edge, right? And that comes from the fact that the shortest shortest paths are made up of shortest paths, right? So if you have, right, we talked about this with Dijkstra. If you have a shortest path from S to T, then every path that is in between, like that makes up that shortest path, is itself a shortest path, okay? For a counterexample, the longest path problem, which you might think is similar to the shortest path. Yeah.
Would that be, sorry, is it going to be the same as like taking the second longest path plus the number of edges for the longest path?
Yeah, so this is why we keep around the shortest. Oh, you're talking about the longest path? It actually doesn't work. So the longest path problem, so if I give you a graph and I ask you, give me the longest path from S to every node, it is actually NP hard, and it is not known. There is no known algorithm other than try all the paths, which is exponential. There is no algorithm people have found out that is faster than that. And the reason is that the longest path doesn't have this property. So the longest path is not necessarily composed of longest paths, right? So if I have a longest path from S that goes through some node V and then gets to T, if this is my longest path, it is not true that this is the longest path to V and this is the longest path to T. Why? You could have a single edge that connects these two. That is, well, I'll let you guys think about as to why that's not true. But because that's not true, you cannot use dynamic programming, which means you cannot get a good algorithm, a polynomial algorithm. And you guys, maybe it's a good exercise to think about why that's not true. It is not in your homework, but you should think about it. And here, yeah, so, but for the shortest path problem, it is true. So that's why we can write this like update equation where we rely on the answers we had to smaller problems in order to solve the bigger one. Basically, what I'm saying is if you had the answer for the longest paths with at most I edges, that does not help you compute the longest path with I plus 1 edges. Turns out. Okay. So element 1 of dynamic programming is you're looking for optimal substructure. Okay. So again, Fibonacci, shortest paths. There's a lot of examples. Anytime I give you a problem that's dynamic programming, your first thought should be, how can I break this into smaller problems? And what are the smaller problems that I can put together to give me the answer to the original problem, right? And again, usually you're doing optimization, so it's not that hard to break it down because the smaller problems are themselves like optimizing for the shortest path or something, okay? We'll do a lot of examples for the next couple of lectures, like 5 or 6 of dynamic programming across many different areas, so you'll get a little better sense. Now, the other thing where dynamic programming can be very helpful is if you just have subproblems, that is just divide and conquer, okay? Now, the reason dynamic programming helps is if your subproblems overlap with each other, if there's a lot of overlap. So for Fibonacci again, right, when I compute I plus 1 and I plus 2, they both use f of I, right? And a lot of different I plus X all use f of I. So f of I gets reused by a lot of the problems up the stack, right? Similarly, for Bellman-Ford, d of I plus 1 will directly use d of IV, but so will a lot of d I plus X. So there's a lot of reusing, okay? So you want a lot of your subproblems to overlap. Again, the example you want to think of is you want to think of this tree, right? Ideally, for dynamic programming to apply to your problem, not only is it possible to break it down into smaller problems, but a lot of the smaller problems repeat, right? Cool. So these are the properties, and this is how you use it. So the optimal substructure helps you find optimal solutions to the subproblems using the optimal solutions of the original problem, right? Overlapping subproblems, the problems show up again and again. And then you can use these properties to design a dynamic programming algorithm. And the answer for the dynamic programming algorithm is make a table for all your smaller problems. Like keep a table, keep all the answers around. So anytime they overlap. If you already found the answer, you just look it up, right? And then use the solutions to the smaller problems to give you the answer to the bigger problems. Okay. There's two ways to think about implementing dynamic programming algorithms. These are two paradigms of how to think about it. I really like the top down. A lot of people prefer the bottom up. Okay, we're going to discuss what each of these is. So what we just saw is called a bottom up approach. The one we just saw with Fibonacci is called bottoms up. Why? Because first you solve the small problems, the base cases, 0 and 1. Then you solve the 2 case, then the 3, then the 4. So you're starting from the easy problems and you're building up to the harder problems. Okay. So that's bottom up. What you guys saw, it's called bottom up. Usually for bottom up approaches, you see for loops, you see arrays, you create an array, you run a for loop from 0 to something. Okay. The other approach, for Bellman-Ford, what we saw is a bottom-up approach. So again, you solve the small problems first. First, we started with the base case of if I use no edges, what is the shortest distance? If I use 1 edge, what's the shortest distance? If I use 2 edges, 3 edges, 4 edges, right? What is the shortest distance? The top-down approach, which I personally like, is don't bother with that. Just write the recursive algorithm first, and then keep a global variable or something, some global state, where in your recursion, you look up the answer. If you already computed it, you use that as the answer. Okay. So solve the big problem, recurse to solve smaller problems. Then those recurse to solve even smaller, right? Etc. The difference between divide and conquer is that you keep an array or a hash map that maps your answers to your inputs to your answer. Okay, so here's an example of top-down Fibonacci. Okay, so the difference is first, outside of the function, we define some global variable, some variable that can be accessed by all the function calls, right? So it's not local, it's outside the scope of the function. Okay. And then we define our recursive version, where one of the differences is we add this if statement first. If I've already computed the answer, return it. So if the answer is already in my global array, just return it. Don't do anything. Just return the answer. Otherwise, call yourself recursively. And that's it. That's the difference. Well, two differences. Call yourself recursively, and when you get the answer, put it in the global array before you return it. Okay, so that's how the very first time that this gets called with a new input, it will fill it in. Every time in the future it gets called with the same input, it will just look it up. Okay, so actually this is the exact same as the bottom-up approach, but personally I like this approach because usually I think of the recursive solution, and then this is just saying save your answers. Okay. This is called memoization. Have you guys heard that before? And actually, both the bottom up and the top down approach are usually around the same running time. So there's usually not a big trade-off between the two. A lot of people prefer the bottom up, but I prefer the top down. It's up to you. Oh, here's a good visualization of why memoization works. We call it on f of 8, right? F of 8 is not in our table. So the very first thing we're going to do is we're going to call ourselves recursively on 6 and 7. But what happens is eventually, when this 6 computes its answer, by the time I need it here, it'll already be in the table, right? Because you call yourself recursively and you start with the bottom ones. So the 0 and 1s you already have in the table. The first time you see a 2, which is here, you're going to compute it. You're going to add the 0 and 1. But anytime you see a 2 after that, you're just gonna use the answer, right? So it basically does the thing of collapsing the tree into this single straight line. Cool, cool. So what we have learned dynamic programming. We are, oh, okay. If you guys want to stay for one more minute, this is actually kind of fun. This is the last slide, I promise. Why do you think it's called dynamic programming? Yeah.
You're basically using work that you've already done by the so I guess like dynamic in general.
Yeah.
Something dynamic, you're not like you're basically taking.
Yeah. Okay. So I know we're almost out of time, so I'll just wrap up. If you're struggling to figure out why we call this dynamic programming, so the real reason we call it dynamic programming is Richard Bellman of Bellman-Ford fame, okay? He is the one who invented this term in the 1950s when he was doing research at Bell Labs or somewhere for the military. And what he says in his biography is the person approving the grants for his research funding really, really hated mathematics and research. But he felt that he was doing mathematical research, but he didn't want to call it mathematical research. So he decided that dynamic programming was a very cool sounding name that would let him do his mathematics research, and that nobody in the military would be like, we're not going to fund that because it's very cool sounding. So the real story is he thought it sounded cool. So that's how he submitted it in his research grant. And now we teach it to every single undergraduate CS person. So yeah. Oh, there we go. Yeah, this is from his autobiography. It's impossible to use the word dynamic in a pejorative sense, so like in a bad way. I thought dynamic programming was a good name. It was something not even a congressman could object to. It's like, what do you work on? I work on dynamic programming. Okay, great. What do you work on? I work on mathematical research. Like, do we need that? Is that good? Yeah. So anyway, see you guys. Oh.